Great. Welcome in, everybody. Thanks for joining us for another N3AS seminar. Today, we're excited to have Benjamin Wallisch with us from Stockholm University and UT Austin. And today, Benjamin will be telling us about free streaming neutrinos in the early universe. So please take it away.
Yes, thank you very much for the invitation and for the introduction. I'm very pleased to talk to you over Zoom about some ongoing work with Katie Fries and PhD student Gab Montefalcano, as well as some older work that has been published together with Daniel Baumann and Daniel Green, as well as both of these Daniels, Florian, Raphael, Anjay, Mariana, and Christoph a few years ago. Generally on the topic of testing some properties of neutrinos, particularly their free streaming nature, just prior to recombination. And so if you have any questions, please go ahead and just raise your hand. I think I should see that, and then we can directly take it there then. Or I'm also very happy to take the questions afterwards. So just to get us started, I want to just flash the current status of constraints on radiation density in the universe. So in the standard model of particle physics and cosmology, we have photons and neutrinos that are relativistic in the universe, and hence contribute to the radiation density. And so we generally parameterize it in terms of this equation at the top, where we write it in terms of the photon density, which is just set by the CMB temperature, as well as the parameter N effective here. That's normalized so that it would be 3 if neutrinos decouple instantaneously in the Earth universe. And so we have two kind of prime measurements of an effective, and hence the radiation density in the universe. One comes from the CMB anisotropies, especially Planck, from which we have a roughly 5% measurement, as well as from Big Bang nuclear synthesis and associated measurements of the primordial abundances of light elements, which gives a similar measurement at the roughly kind of 10% level. Now that's great, and so that's really kind of measuring the energy density of neutrinos. But the question is, are we actually seeing neutrinos via gravity, or might we see something else? And so I think there's 3 properties of neutrinos that are particularly important when we talk about gravitationally measuring these particles. One is, as it was just saying, they are just the energy density. And so the measurements, as it just showed on the previous slide, they are consistent with the expected number of a bit more than 3. Now, neutrino masses are another property. So far, we of course haven't detected a non-zero neutrino mass, even though we of course know from oscillation experiments that they are. However, if we talk about early universe cosmology, then they are not important given the current upper limits on neutrino masses from cosmology. Thirdly, we expect that these particles decoupled from the rest of the standard model, in particular the photons and electrons in the early universe, at a time of about roughly 1 second after the Big Bang, or roughly order of kind of 1 megaelectron volt of temperature. And so the question I'm asking for the next 20 minutes is, and what I want to answer is, can we detect this free streaming of the neutrinos in our data? And particularly, I will discuss this in the context of both the cosmic microwave background as well as the larger structure of the universe. So starting with the CMB, or more specifically the CMB anisotropies, as they are shown here on this great map from a Planck satellite, which shows temperature fluctuations at the level of 1 in 10 to the 4 that we see in our data. And so what we see here is if you measure kind of the 2-point function of this map, we just look at the angles, kind of sum up all the correlations of particular kind of angles in the sky, as they're here on the upper axis, the angles. We can transform that into multiples and on the lower axis. And so if you compute the correlation function, then we have this very nice power spectrum where we see this overall damping on small scale plus these oscillations on top. Now, what are these oscillations? Well, in the early universe, photons and baryons are very strongly coupled to one another. In addition, perturbations seeded by inflation or some other mechanism excited sound waves in this photon baryon fluid. And so that, as a lot of things in physics, can just be described by a simple oscillator equation that's shown here in the center of the slide, where we have the photon perturbations being sourced by gravity, as well as kind of pushed around by just the photon pressure. What is sourcing this on the right-hand side? This phi is a combination of the neutrino potentials, which receives contributions from all components that are present in the universe at a given time. So in particular, baryons, photons, neutrinos, and dark matter just gravitationally, quote unquote, talk to one another, and hence through that equation to the photon perturbations. Solving this equation, of course, gives us nothing else but acoustic oscillations that are schematically shown kind of down here, where I'm actually set the sign solution of this equation to 0 by assuming adiabatic initial conditions, which just leaves us with the cosine solution. Especially, we also see that the sound speed of these waves of the photon perturbations is given by speed of light over 3 times this contribution coming from baryons. And so these are exactly the oscillations that we see in the CMB power spectrum. And so we don't only see those in the temperature anisotropies that are shown here at the top with the map and the power spectrum on the left-hand side, but we also see that in the polarization map, or if you then compute the 2-point functions, both like the auto correlation of the polarization, as well as the cross correlation between temperature and polarization. And so this is really kind of one of the prime signals that we are measuring when we look at the CMB. Coming back to neutrinos, I was already saying, given this equation earlier of the radiation density just being the sum of the neutrino and the photon energy density. And so in the early universe, neutrinos make up 40% of the radiation density, the rest being photons. And given that in the early universe, during radiation domination, that's roughly about the amount of energy density that is relevant, these neutrinos leave a sizable gravitational imprint, which means that we can just detect the energy density through the gravitational interactions. And so in particular, we see that if we increase the amount of radiation in the early universe, or in the universe more generally, we see that there's more damping if we keep the first peak or the sound horizon or the angular size of the sound horizon fixed, because it's very well measured in the data. So that is just kind of an effect that we have from the background evolution of the universe. In addition, though, now we can ask the question, okay, what distinguishes free streaming from non-free streaming neutrinos in our observations. Now, free streaming neutrinos means that they are traveling ahead of the sound horizon because they're not bound to like the photons and baryons after that decoupling, which means they induce metric fluctuations ahead of the sound horizon. And so what I just like depicted here at the bottom is, imagine you have just an overdensity kind of in the center. The dark matter is just kind of sitting there, not doing much. Photons and baryons, as well as the neutrinos, feel their graduation pressure and are driven outwards, with the neutrinos being ahead of the photons and baryons. Some more quantitatively, here I'm showing the same thing, just the radial profile, and we see that so what's shown here is the mass profile of the perturbations. So it's the perturbations times the radius squared, just to enhance the larger radii. And so we see that the dark matter is staying behind, whereas the photons and baryons, as well as the neutrinos, kind of move outwards, with the sizable fraction of the neutrinos being ahead of the photons and baryons. And so if we kind of compute the effect on the CMB power spectrum, we see a number of changes, but in particular, we see a phase shift, which means that, so here on the right-hand side, I'm showing like the same solution to the oscillator equation that I showed earlier, but now this cosine solution acquires an additional phase. And so this is illustrated here on the left-hand side, which shows that if we increase the number of free streaming degrees of freedom, the peaks of the CMB temperature power spectrum move to larger scales or kind of to smaller multiples. And this effect actually has been detected in Planck 2013 temperature data by Wallisch et al. Quite a few years ago. Now, what is very interesting is that free streaming neutrinos are a causal way to produce such a coherent shift in the peak locations, with essentially the other possibility being isocurvature fluctuations. So in the present, if you assume adiabatic fluctuations, then it's just a free streaming species who can induce such a coherent shift, which means that is a pretty pristine and interesting signature of the free stream nature of radiation. And so what we can do is we can measure the size of this phase shift as a function of multiples of the CME spectra, not only in temperature, but also in polarization and in the cross spectrum. And this is some work that I'm currently doing together, especially with Gab Montefalcano, where we kind of measured, following et al, the shape of this phase shift, which you also understand analytically, especially kind of at high multiples, which are modes that enter the horizon during radiation domination. We expect a constant phase shift. And so this is exactly what we see here. And now it shuts off towards lower multiples or modes that enter the horizon, especially during meta-domination, because then the radiation density is becoming more and more of a subdominant contribution. And so the neutrinos can't have as large of an effect anymore on our observable. I see that two hands raised. I'm not sure who was first. Let's go with Emma first.
Sure, yeah.
Yeah, I have a question. So on the previous slide, why do you see in one scenario the phase shift, and in the scenario that you showed before, you see an amplitude shift when you increase delta effective? Like, how can I understand this? Yeah, here
so
you see the amplitude changing, and in this case, you see the phase changing. Yeah.
So in this figure here, free streaming neutrinos, or free streaming ineffective, has four main effects. One is it changes the sound horizon, so it changes the frequency, and so I already set that change to 0 by fixing the angular size of the sound horizon, theta s here. The second effect is what we see here in this plot predominantly, which is the overall damping, which also comes from the background evolution. In addition, from the perturbation side of things, we do have an amplitude shift. So the final crystal oscillations are here. So the size here is, the amplitude here changes, which I already undid as well by kind of fixing the amplitude. And then the fourth and smallest effect is a phase shift. So all of these things are happening at the same time. It's just that in this figure here, I set the first three to essentially 0 by changing by fixing these observables or parameters, and then the phase shift really becomes visible.
Okay, so you always have these effects, but you just chose these two different scenarios to make it clear.
That's right. So we always have these effects, and if we use just if we constrain an effective in our data just by looking at an effective by itself, then all of these effects contribute. Now, what I'm saying here is we can particularly look at the phase shift as one of these effects. Kind of just take that out of kind of all these effects. And just look at the phase shift as a kind of pristine signal for kind of the free stream of nature, given that other effects on the CMB can easily change the damping, just change like the Hubble scale or the helium fraction, for instance. Of course, you can easily change the sound horizon, and also the amplitude of the BEL, for example, through a change in omega b. So that's why I'm just looking at the phase shift, which is pretty unique.
Great, thank you.
And Brian, you have another question?
Yeah, thanks, Ben. If you go to the next slide, yeah. So is this real data? And if so, is there a cut sky? Because I would imagine, just a moderate cut for the galaxy would blend together, enough delta L's and subsume their phases into one another that it'd be pretty hard to see a delta L of 1, as you seem to be indicating. So yeah, is it real data? And if so, what's the cut?
So this plot is not real data yet. So here it's just kind of theoretically extracting the size of the phase shift given a change in an effective. And so these dots here are extracted by looking at 100 cosmologies with different values of n effective, and then kind of rescaling them according to this equation at the top, where kind of A essentially is just the ratio of energy densities with respect to kind of the fiducial, which is just the standard model value of n effective. And then by sampling all these 100 cosmologies, we also can get these error bars that are shown here. So at the moment, that's just kind of theoretically speaking, or theoretically extracted by running camel class.
Thanks.
And then the data is coming on the next slide.
Okay.
Then any other questions on the theory side? Okay, then we move on to the data indeed. And so as I was saying, Wallisch et al. Extracted in 2015 or detected this phase shift effect in temperature data in 2015 by measuring kind of an energy density equivalent and nu caused by the phase shift at more than 5 sigma. What we have done now is we look at Planck 2018 data on the one hand, just in temperature. That's the gray curve here on the left hand side, which is already somewhat more constraining, especially on the positive side. Then in particular, we now kind of did a similar exercise kind of extracting the phase shift not only in temperature but also polarization, as I was showing on a previous slide, including that in an analysis. Then leads to the the blue posterior here with smaller kind of error bars. So we do see that by adding polarization data, we do get a sizable, sizably better constraint, which has, of course, it's just additional data, but in addition, the peaks in the polarization spectrum are sharper than in temperature, given that they're just a snapshot of essentially the last scatter of at the redshift of 1,000, and not like the last few scatters as in the temperature spectrum. And then in addition, if we add data from Actin SPT, we get an additional decrease of the error bars by roughly 30%. And it's especially kind of if you look ahead, we also kind of ran a few forecasts for the Science Observatory as well as kind of CBS4. We see that we again get roughly 40% improvement for SO and another kind of factor of roughly 2 when you go to CBS4, just because we're measuring additional oscillations to smaller and smaller kind of multiples, especially in the sharper case of polarization. In addition, we can, so these constraints here were assuming that we just have an effective being the standard model value from neutrinos. Now, if just intends just asking like how free streaming are neutrinos, and we see, well, they're pretty free streaming, consistent with like all of them, all 3 species being free streaming. In addition, we can ask the question, well, what if you additionally vary kind of the energy density away from 3, asking what about like all potential kind of radiation in the universe that's not in photons, and that's kind of shown here on this plot, where we have like an effective on the horizontal axis, and then the value associated with the phase shift on the vertical axis. And again, we see it's consistent with all 3 of them being free streaming at roughly the 1 sigma level. What we're doing in addition at the moment is, apart from kind of running these forecasts, we also look at a different way of extracting the phase shift, not based on the spectra, so the CLs, but actually looking at it at the level of the perturbation, so the delta gammas, which would be kind of even cleaner signal, a cleaner way of extracting these observables. So much for the CMB at the moment. Are there any questions regarding this part before I move on to large structure? Yes, 2 questions. Susan?
Oh, thank you very much. I just cannot resist asking about whether or not the actual phase shift effect you observe is could reasonably be interpreted in any other way. When you first introduced it, you said the free streaming neutrinos were a causal way of generating such a coherent shift without actually stating it was a unique way. Therefore, I was wondering if you might comment upon other possibilities of interpreting this parameterization of the data.
Yeah, so the fact that we acquire kind of a phase here of the oscillations we showed kind of a few years ago. Essentially, there's two ways of doing that. One way is by having a species in the universe that is propagating information faster than the sound speed in the photon baryon fluid, and so the only kind of physical way that I'm aware of is essentially kind of free streaming radiation. The other possibility is that we have isocurvature fluctuations in the universe, and generically, what we find is that these isocurvature fluctuations then are associated with a pretty strongly scale-dependent phase shift, rather than this, especially kind of deep invalidation nomination, kind of constant phase shift that we see in for neutrinos. So in that way, I think associating a phase, especially with this shape here, and especially kind of this essentially kind of constant piece for kind of L's larger than say like 1500. That's pretty unique for free stream radiation.
So very good. It's the way the data presents itself makes it clear that the free streaming neutrino interpretation is proper.
Yes.
Thank you.
Okay, and Anna?
Hi, Ben, it's George Fuller. So,
Oh, hey.
just a question. So I think in this part of the talk, you know, all you really needed was an adiabatic fluctuation and then for this neutrino component to be free streaming.
Yeah.
I'm wondering, and maybe the second part of the talk won't be this way, but you know, if the relic neutrino energy spectrum is not a thermal shaped Fermi Dirac blackbody, but it was distorted in some way, you know, by something, dilution event or something, then would that make a difference? And probably not at this stage, right? Because you just want them free streaming. You want them moving at basically the speed of light. But if they have mass, I would imagine that you might actually be sensitive to what the actual energy spectrum is, the momentum spectrum.
That's a good question. So indeed, if in so the what we're essentially sensitive to is like the modes that enter the horizon at times that we see here in the CMB, and so at those scales, like the neutrino masses are relatively unimportant. I haven't thought about neutrino kind of spectral distortions effectively, but I don't think they, especially at the sizes of effects that we're talking about here, that they should have a sizable imprint.
And certainly not the standard model ones.
That's right. Now, what I know is that if it did have like very large neutrino masses, by some way, I mean, in principle, they're excluded by cosmology, but imagining like neutrino masses above 1 eV or so, then the size of the phase shift would be affected, given that they would become non-altruistic kind of earlier, and hence the phase shift imprint will be different. But for the neutrino masses that we have currently constrained, I don't think that should make much of a difference.
Very good. Thank you.
Sure. Okay, so with that, let's move on to large-scale structure. Let's kind of, like I showed this kind of movie of the perturbations in the early universe kind of earlier for the CMB. Now, of course, that evolution continues, and kind of at a redshift of about 1,000, photons and baryons decouple, and so now also kind of photons are free streaming, and so that's what's shown here in these 4 panels. Within the end, what we're left with is this very characteristic peak of the baryon-Acoustic oscillations at the distance of about 150 megaparsec. And so, given that all of this is a coherent and causal story, I expect you already see where this is going with the phase shift, baryon-Acoustic oscillations, and large-scale structure. But before going there, there's quite a few different observables of large-scale structure, especially kind of galaxy clustering, where we can precisely measure the location of galaxies in angular positions as well as kind of redshift, and can then kind of make these maps of effectively the kind of biased a bias map of the underlying density distribution, matter density distribution. We also have reglensing, Lyman alpha forest, galaxy clusters, various kind of CMB secondary probes that we can use to observe larger structure of the universe. I will particularly going to be focusing on galaxy clustering as measured by BOSS until a few years ago. And so if you again compute the 2-point function of essentially this map that I'm showing here, and in Fourier space, we get the matter power spectrum that's shown here on this slide on the right-hand side, overlaid with inferred measurements of this power spectrum from various data sets, as well as projected onto the linear version. Now, I don't want to look at the entire matter power spectrum, in particular, given that on small scales, we have to contend with nonlinearities from gravitational evolution. But I just want to look at a part of the spectrum, especially I want to look at it when I'm decomposing the overall matter power spectrum in a kind of smooth part that's just that your eye picks up on the left-hand side, as well as kind of a wiggly, like the oscillatory part kind of on top, which is then kind of shown here on the right-hand side, which I'm calling the spectrum of Baryon-Kutzke oscillations. And so this is kind of very useful because, in particular, it captures the sound waves that we also see in the CMB. It's sensitive to the same kind of effects in the cosmological evolution, including the primordial initial conditions. And most importantly, we have very good theoretical control over the effect of gravitational nonlinearities on this part of the matter power spectrum. In fact, we can just compute what the effect is. In particular, what we see from large-scale bulk flows is this overall kind of damping of these oscillations. And so, coming back to the phase shift, given the story that I've been telling you in the CMB, as well as kind of continue that movie of the perturbations, I guess it's no surprise they will tell you, well, if you do the same exercise in the BEO spectrum and extract the effect of kind of varying amount of free stream radiation, we also see that the peaks coherently shift to larger scales or to smaller k, similar to the CMB. And if you kind of closely inspect it, again, we find that it's the phase shift that is with a similar or with a consistent amount as we see in the CMB. Now, I was already telling you about the gravitational linearities that we have to deal with in larger structure, opposed to the CMB, which is mostly linear physics. What's very nice, though, about the phase shift is that it has been shown that, especially a constant phase, is immune to the effect of gravitational nonlinearities. So while the amplitude and the frequency of the Baryon-Kutzke oscillations are affected by the late time nonlinearities, a phase is protected, which essentially goes back to locality and rotational invariance of the observables. What this means is that we can actually use the linear prediction for the phase shift in order to kind of look for it in nonlinear data. And so that's quite a luxury. And so that's why we propose to adapt kind of the standard BAO analysis, which essentially just constrains the frequency of the Baryon-Kutzke oscillations with this parameter alpha by kind of adding the phase to it, again parameterized by an amplitude, as well as kind of the shape with a template that we again extracted using kind of Boltzmann solver, in this case class, similar to the figure that I showed you for the CMB. And so with that, we did that analysis in BOSS And so that was the result. We knew that it would be kind of a very degenerate measurement, given that we want to measure both, back to one slide, given that we want to measure both the frequency and the phase, just with a few peaks and troughs in the BO spectrum. And so this is why we used additional data from the CMB but only kind of to put a prior on the frequency, so the BO frequency or the sound horizon, and then kind of measure the phase in this way. And so that's shown with these kind of red and orange controls for the two redshift bins of the BOSS DR12 data set. And in that case, we found a non-zero measurement at more than 99% confidence. However, given that the small offset of the mean values between kind of BOSS and Planck for the BO frequency, we're kind of driven kind of to larger values of the phase. But overall, so this is, I would just say that this is kind of proof of principle that it's possible to extract information on neutrinos from galaxy clustering data. In particular, at the moment, kind of with BOSS, that's just showing that it's possible. But if you go to future data, in particular, for instance, kind of DESI and Euclid, we see that this will kind of improve by factors of a few, and actually then will be kind of meaningful in its own right, independent of what exactly is going on with kind of the potential kind of CMB prior. And especially like DESI and Euclid are currently taking data. So such a measurement could potentially be made in the next 3 years. And then an even more futuristic survey, as is kind of indicated by these green and red lines, could really kind of put a measurement at the even like 10% level from galaxy clustering data, which I think is pretty exciting in its own right. And so with that, I'm happy to conclude by saying that I think, very generally speaking, I think as a cosmologist, it's very exciting that thanks to the theoretical insights that we have gained into the CMB and large structure power spectra over the last 2 years, as well as the observational control that we have now over these observables, we can really kind of reliably extract more information about the underlying physics that we have in the past. And so here, kind of in the last half an hour, I gave kind of one example by showing you that we can see that neutrinos are indeed free streaming prior to recombination, thanks to the phase shift as a robust signature. And we see that, as it looks like from the phase shift, these they are indeed free streaming according to the standard model. And so on the flip side, we can then use that to constrain non-standard neutrino physics, such as kind of self-interactions or interactions with other components of the universe. And overall, I think it's very exciting that very nice improvements, both on the CMB and large structure side, are indeed forthcoming. And so with that, I thank you very much for your attention, and I'm happy to take more questions.
Great, thank you, Benjamin. If we have more questions, please raise your virtual hand. We have a question from Julien. Please go ahead.
Hi, Ben. This is Evan Groves.
Hey.
A question, from looking at these plots that you were showing with N delta 5 versus N effective, it seems to me, right, that there's not a lot of preference, but possibly, N effective less than 3. If we were to just, using that conclusion on your last slide, it just fix N delta phi and N effective to be equal to each other. Is there anything we can do about like tightening the error bar to, possibly smaller than, the 10% or so that you showed earlier?
Yeah, I mean, so here, so this is, I guess this question is in particular interesting in the context of the CMB constraints. So this posterior here on this slide was just taking the slice at an effective of 3.044 here. And so the question I guess you're asking is, what if you can take a slice here on the diagonal, kind of fixing an effective to be the same as the phase component? I think that posterior is slightly wider, but certainly a very interesting question to ask. And indeed, it is, especially kind of when including ACT data. The posterior in that case is driven to smaller values, but that's something we already see in the standard kind of ACT analysis as well. Kind of Planck and SPT do prefer slightly larger values when effective.
Okay, so does it do anything to the error bar if you take that diagonal kind of cross section?
I think the error bar is slightly kind of wider than if you kind of fix an effective to be 3, but not that much.
Okay, thank you.
I do have a related question. So what would be the physical explanation for NF delta phi to be different from the x-axis NF, which I guess is just the energy density one? What would be the origin of that?
Well, that would mean that, so as for example, if kind of on the vertical axis you would see 2, and on the horizontal axis would be 3. This would like one basic explanation for that, or interpretation of that, would be that 2 out of the 3 neutrino species are free streaming, with kind of one of them being non-free streaming, or having a mean free path that is smaller than kind of the Hubble radius. Similarly, I mean, if it's a fractional amount, then it's maybe kind of a bit more complicated. It's like it's not maybe not completely free streaming, but there are kind of some small kind of interactions that decrease the phase shift slightly, but not kind of all the way, or something similar. But so overall, essentially, it just means that if the vertical axis is smaller than the horizontal axis, that it's not completely free streaming, the radiation that we see in the observations.
And the opposite would mean that you have some extra free streaming thing that is not contributing to the energy density?
I'm not sure what that would be. So yeah, I'm not sure what. I'm not sure what that would be if kind of the vertical axis would be larger than the horizontal axis, physically speaking.
Yeah.
Do we have any other questions for our speaker? I don't see any more hands, so let's thank Benjamin again.
Thank you all very much for the invitation again, and the very nice questions.
Thank you.
Bye, everyone.